Now that we've made a lot of headway in our understanding of circuits, I'd like to go back a little bit to some more fundamental considerations that will help us really understand the next circuit element that we want to introduce, the capacitor, which has an ability to store energy. But we have to come back now to this topic that started this whole discussion, namely the topic of energy, and in particular, the topic of potential energy. You'll notice that so far, even though we started with the idea of potential energy, we've really been mostly talking about work and voltages. We kind of dropped the thread on the potential energy concept as a concept all by itself. You will recall that the mechanical definition of potential energy that we gave you was that the potential energy of an object at any point x we can get by defining it or computing, right, the work needed to be done by us in order to get the object at point x from some standard agreed upon reference point. If we want a diagram, over here I'm going to have some reference point, REF, right, and that I just agree upon by convention, and then over here is going to be my point x, and I'm going to drag my particle from the reference point to the point x, doing a certain amount of work. And the idea is that, well, if energy is conserved, then that energy that we've done and invested in our system is then now energy we can potentially get out in the exact amount that we've put it in. So that is the potential energy of the object at point x. Now, that potential energy, this is a general result from mechanics. We specialized our considerations to electrical systems by thinking about what happens if the object we're moving actually happens to be a charge, which we typically were calling Q. So if I look at the potential energy then of a charge Q, it's equal to this amount of work. But what we've been doing so far involve voltages. And for voltages, those are directly related to work. We know that the voltage is the work per unit charge. So to get the work required to make this motion for my charge, all I need to do is to multiply the charge, because it's proportional to the charge, times that proportionality constant, and that proportionality constant is the voltage between the 2 points. So the voltage to take me from this reference point to the point x. Now this function here is kind of an interesting function. It's voltage, as we've been working with it, but what's interesting about it is that because we're going to agree upon some conventional starting point, what we're left with really is just a function of position x. Let's think about this for a moment. Suppose I were to actually measure this with a voltmeter. So I'll have my voltmeter here, V, and as you know, the black wire here, or the minus or the ground lead, is where the starting point would be. So I'm going to always nail that lead down to that reference point. I'm not going to, for these considerations, let that negative lead move anywhere. Then what I want to do is I want to take my positive lead, which is usually colored in red. I'll label it here also with a plus to remind us. And I'm going to take this lead here, and I'm going to be moving my lead now around all over space at all different positions x. Sometimes I'll actually take it to my point x, other times I might move it somewhere else. And what I'm doing is I'm studying the reading on my voltmeter as I just move the red lead around to different locations. Here, I'll just label them x here in red. So what I'm left with then, if you think about it, really is just a function of x. So there's a special name we give to that function. It's not too different from voltage if you really think about what we're doing. It's just voltage where you've agreed to set one particular reference point. So we typically denote that as the same letter, V, of x. But now that it's a function of just a single value, this has a slightly different meaning because the way we're keeping our reference point fixed. And this is given a special name then. This is sometimes called the electric potential. It's sometimes also called the electrostatic potential. The two key words, though, in whichever term you wish to use, the two key words are potential, you see, because it's very closely related to potential energy, and electric or electrostatic, right? That electric word tells you it's an electric quantity. And just like all of our electric quantities, like the electric field, we take what is normally thought about in mechanics class, for instance, the force, and we do it force per charge. In this case, it's potential per charge. And in fact, you can see that because we could solve this equation here. So one version of this equation says if I want the potential energy of a charge Q at location X, I would just multiply this electrostatic potential by the charge Q. We, of course, can also turn the equation around and say, well, the electrostatic potential at location X is equal to the potential energy that any charge Q would have at that location, but it's per unit charge. It's divided by charge. It's on a per unit charge basis. The final way we can look at this set of relations is the basic definition of V, which I had basically given to you right here, but it's always nice to have it written back down again. You can also determine the electrostatic potential as the voltage to the point X from your given reference point. And we, of course, also have had nice integral definition of that. This now is a definition of voltage, so it's minus, because it's associated with work done by us, the integral from our starting point, but it's always going to be the same starting point, to our final point X. And then what we're integrating is not force times distance, because this is an electric quantity, so it's just the field dotted then with your displacements dx, like so. So this kind of now sets the stage for new considerations about potential energy that we will be taking up in our future discussions. It's just helpful to have these relations all laid out here together.